I cannot see more than one.
Oh, maybe we can address towards the end, or if you
Okay.
like, you can go through. I can also read out the queries now if you want.
Okay.
Yeah. So the very first one, uh, it was from Mr. Rajesh Chaurasia. Does quantum phenomena manifest more with more and more lower size, like size of atom, size of electrons, etc.? If yes, then won't trapped ion will need to think of more mini scales?
Uh, no, okay, so it is not clear the question. Like, but if you go to more and more, reduce the size, then quantum phenomena will start to observe, like superposition, quantization, all these things you have to take care of. So that is what I want to say. Because you are reducing the size of, I think this is with respect to the size, what I was telling, the transistor size. Now, like nowadays in Pentium, it is around 10 to the power 11 numbers of transistors there inside a small processor. So the size is around like a few microns. So the atom size is around 2-3 microns. So it is at that level. So like now, if you go to that size, then yeah, quantumness we start to see. We start to observe that quantumness.
Okay. So then there was another question from K. Lakshmi Narayan Simha Rao. Can you please explain the quantum superposition? And
Uh,
in continuation, he also asked how to visualize the superposition.
Experimentally, it is easier to visualize. I mean, at a time, you can measure only one state. If you measure the state, then you got the information. Like here, if you apply pi by 2 pulse, as I was discussing here, so pi by 2 pulse meaning what? Like 50% population will be supposed to transfer from that state, from S to D state. But that, if you measure it, because the superposition state is what? You can write it in terms of alpha 0 ket plus beta 1 ket, right? Now, what like probability amplitude will give you the value, exact value, how much it is there. So it is probabilistic, probability value. Mod alpha square will give you the like how much probability is there in A state and how much is B states. So that is basically superposition state mathematically. Yeah. Experimentally, the way we usually do it, now if we apply pi by 2 pulse, it's supposed to be 50% population will be in A state, 50% population will be in B state.
Okay, so Dr. Bhavesh Deka, uh, he said, can you define a coherent QT system?
Oh, can I define coherent system? That okay, experimentally it is easy to see, because if you see the Rabi oscillation for longer time, you can see the contrast is going down. Is not always going to 0 to 1. The contrast, like the other slide what I was showing, the contrast, you can see it is going down each time. So that will tell you it is not coherent state anymore. The system is not in, its coherence is lost. So that experimentally it is easily understandable. So there are few methods, like one is Rabi oscillation, then other one is the Ramsey spectroscopy. Those things we can do to check like still the coherence is there or coherence is lost. That will be quick.
Okay. So Mr. Venkata, uh, he want to ask, what is the maximum coherence time in case of trapped ions?
Okay. So, okay. I mean, in general, like all over the world, one group from China, they have shown it is almost an hour, which is huge compared to other candidates like superconducting, which is also at the forefront. Though they are using synthetic qubits, in their case, it is still, I would say it is millisecond, but it is not millisecond, but less than millisecond. But in my system, it is 6 milliseconds. It is not, 1 hour. But people have observed in trap diamond, the ion was ytterbium ion. They have done it up to 1 hour.
That's huge, actually.
Yeah, that is huge. That is huge. But the thing is that I don't know the details. What kind of experiment they were performing? That's also related. Okay. So if only they were observing the rabbi, no other things. And one more thing is like if your transition is magnetic field insensitive, then also that is somehow it will help. In my case, all these states are Zeeman levels. So it will not be insensitive. It's magnetic field sensitive. But if you go to hyperfine, there you can find state which is magnetic field insensitive. Because in this kind of setup, most of the noise comes from magnetic field as a stray field. So yeah.
Yeah, so another message from K. Lakshmi Narasimha Rao. Probability of cat 0 and cat 1 and simultaneous existence are different in connection with superposition.
Superposition state you can write in terms of alpha ket 0 state plus beta ket 1 state. Those are coefficients are complex quantity. So if you do like if you get the probability amplitude, so if you square the coefficient, then you will get the like how much percentage is there in the 0 state and how much there in the 1 state.
So actually, he wrote long justification also. I am trying to understand the superposition. Probability of finding cat 0 or cat 1 at any one instant is different from simultaneous existence of both at a time. Not
Simultaneously,
able
it
to
is
understand the superposition. Literature explains the superposition with probability of finding either of them as superposition. You may please throw some light on this. How is it practically achieved? But I can also correlate with tossing coin in the air at every instance. It keeps changing and we can not differentiate the instants. So conclude it as simultaneous existence of head and tail. Is it the same here also?
no. When you are talking about head and tail, you cannot have simultaneously head and tail. Okay, so that is deterministic, either head or tail. How many times you toss, either you will get head or tail. You cannot get simultaneously in one throw head and tail is swing. This is not possible. In quantum, what I'm saying or what is there, like it you cannot measure both state simultaneously. But if you measure one state and you are getting the probability is 50% or whatever 20%, 30%, that means where is the rest of the population? It has to be in other state. So
Okay.
yeah.
So one more query from Senthil Kumar. Is this qubit store information?
Qubit store information, but it is not the way classical bit stores. This is bit different.
Okay.
Yeah.
So one more suggestion from Prasad for you that if possible join with mobile also so you can see the chat directly. So possibly we need to log in on two systems, then one we can
Yes.
use for talk, another
Mobile,
one
sir,
for
it
chat.
is mobile. It is very problematic because inside UAE, if network so bad, you will not realize. So
It's okay, fine. We
yeah.
can manage like this. And the last query is what kind of atoms they use to create 1 hour coherence time?
Oh, that is ytterbium.
Ytterbium atoms.
Yeah.
Okay. Okay, sir. So that's all the queries so far. There may be more queries towards the end of the lecture. So
Okay.
uh, now we can continue with the lecture and later on we will also see some more queries. Okay, sir.
Okay. Okay. Thank you. Thank you for the
Okay, sir.
questions. Maybe I tried to answer. Maybe I don't know whether I satisfy you or not. But yeah, whatever I'm understanding, Okay, let me continue. I'll be a bit more faster because I have to explain some things, application of competition and sensing and all these things. So yeah, so we end it over here, Rabi oscillation, but now you can see, so what you are seeing it over here. So if you have iron now and you are driving the quadruple transitions, you will see the carrier spectrum. So the top right side, you see all the spectrum, but you are seeing not only carrier, you are seeing also the sidebands, motional sidebands, motion of atoms. When you have more than one atoms, then you will have more motional modes. Like here, as an example, the bottom I am showing like all the simulation how it is oscillating, but on like at the middle you can see the image of ion which is moving. One is center of mass motion along the axial direction. Axial confinement is done by using static voltage, and the other one is stretch motion. You can see, yeah, those two are from image from the real trap setup. So now you know, so like if you have a particle in space, you know it has 3 degrees of freedom, right? Along 3 directions. So it will have 3 different motions. Similarly, here also, this is trapped in a space, so it will have for one atom 3 different. But when you have a more than um, one atom or more than one atomic ion, then it will have a different kind of motion. Some of the motion has already been figured out, like one is stretch mode, zigzag mode, tilted mode also. It is not shown here, but those modes are, already been identified a long time back in the literature, and there are some modes still available which is not been in the literature. It is not there. Those are like kind of complicated mode. So what I'm pointing it out over here, like not only you have carrier peaks in your spectrum, you will have motional peaks. So that is the important thing. So you can, if you want to make a qubit, you can make a qubit with motional states also, though it is less prone to noise. Now, I will just tell you a little bit about laser ion interaction, because so always we are talking ion through the laser, right? And this is the Hamiltonian. You all know, like the Hamiltonian, which is from the atom, and then this is coming from this Hamiltonian is coming from the laser, which you can write in terms of laser is basically oscillator, right? In terms of basically raising and lowering operator, and this is the interaction field. This E is basically the interaction field, which is like you can write in terms of the second quantization form. And then, so if you simplify there, so here omega L is the frequency of the laser, and omega 0 is the like the energy difference between two levels. And so from that energy, you know the frequency, what frequency you need to drive the transition. So that omega L has to be very close to omega 0 so that the population will be transferred. But if you simplify this, then you will see there will be two terms, omega L plus omega 0 and omega L minus omega 0. But we have assumed, or we prepare the system so that omega L has to be very close to omega 0. Now, mathematically, you can use rotating wave approximation, or go to interaction picture. Then you can neglect higher order terms like omega L plus omega 0 terms, so that you can um, stay in this region. So that is what I have shown it over here. Now you can see the the field, electric field vector, what I have written it over here. There is also position dependent. So this X is also very important, and this X you can write in terms of lowering and raising operator. So now when you are confining atomic ion inside the potential, so like in order to keep it for a long time, one basic thing is that the wavelength, what you are probing, that has to be bigger compared to the motional displacement of your ion. If it is higher, then the system is a little bit unstable. So there are many more things regarding the theory, like micromotion is there, and if the motion of ion is higher compared to the wavelength, then like if you want to prepare, then you cannot prepare with 100% efficient. The preparation will be very bad. This like lifetime of iron will be in the trap will be very small. So many more things will be there. So that is one thing I just want to highlight. So the point is that you have to get your system in lambdic regime. So that term is very popular. Lambdic regime meaning the wavelength what it is what you are implementing on ion that is bigger compared to the excursion of ion, like motional excursion of ion. Now. So this is the in the introduction frame. This is the form of Hamiltonian. Now, if you here another term delta. Delta I didn't tell it before. The delta is the detuning. Detuning meaning difference between omega L minus omega naught. So if it is 0, if you plug it into over here, then you will get the Hamiltonian, which tells you the carrier transitions. When it is minus omega, it will be first state sideband, and when it is plus omega, this is going to give you blue sideband. All these sidebands what I'm talking about, it is motional sideband. So when you trap an ion, I can give you an estimate, like depending on the potential. Like in our case, the radial secular frequency, we used to say secular frequency, it will be in megahertz, whereas axial is in kilohertz. But again, both depends on the amplitude of the potential what you are applying, and also the frequency of what you are applying, driving frequency. So here I just showed you, like when you have a free atom energy levels, that is defined by E excited state and G state. But when you have a trapped atom energy levels, then you have those electronic state, but you have also motional state. These are the motional state. N equals to 0 meaning all are motional state. You can think it as is a vibrational state. So N0 means 0 photon is there, and 1 means one photon is there. So in that is the way of representing. Now, so why I'm saying all these things, because next thing, yeah, I'm going to talk about. So you see, like the motional state, you can think as a simple harmonic oscillator, and you want to go from one motional state of a particular electronic state to another motional state of another electronic state. Then you can drive also that transitions, though it has to be very well designed and well developed, all those layers. So the purpose of telling is that why I'm saying this thing, like if you want to prepare your qubit using motional state, it is possible. But the coherence, but if you drive the Rabi oscillation for blue sideband or red sideband, the coherence time will be, there will be much difference in the coherence time. The order of coherence time will be completely different. So this is also another one thing, like technologically, this has to be very advanced. Like Doppler cooling is always there. Like when you are trapping, that time Doppler cooling, like Doppler lasers are already on, so that you can bring the ion to at least 10 phonon, 10 in between 10 to 50 phonons. So if I tell you in the temperature regime, it will be around millikelvin, less than 10 millikelvin. Now, depending on the kind of experiment we are going to perform, we have to adapt a similar kind of cooling method. So one is Doppler cooling is there, but then if you want to reduce the average phonon number, or if you want to go beyond that temperature, then there are PGC cooling, polarization gradient cooling, and EIT cooling is also there. And the other one which we used to use, resolved sideband cooling, which usually brings the ion to its ground state, ground motional state. So for quantum computing, it is if you prepare your state in a ground motional state, then you can work for a longer time, and the result of the fidelity, get fidelity, is better. If you start from higher motional state, then fidelity is not as good as when you prepare in ground motional state. Okay. The other technology which actually characterizes our system, how good it is Ramsey spectroscopy. So Rabi oscillation I discussed, that is driven oscillation, right? We are driving the transitions, but Ramsey is a free evaluation. Why it is called free evaluation? Because you prepare the system in a superposition state, like you apply by 2 pulse, so that you bring the atom to the equator of the block sphere, and then you wait for some amount of time. As I'm like I have written over here, the wait time. So I'm waiting, and then I'm again applying pi by 2 pulse, and then I'm measuring. So let's say if t is equals to 0, wait time is 0, then what is going to happen over here? If I measure the fluorescence, I should not see any fluorescence because I prepare in 0 state, then I apply pi by 2 pulse. So I bring the ion to the equator. Then without waiting any time, I'm again applying pi by 2 pulse. So it will bring to 1, right? But I'm always measuring 0 state. So the population is not in 0 state. So then I will say dark. So it will be dark state. But if I increase this wait time, so then I can, I want to check how the evolution is happening, because when it is at the equator, it will be prone to get the noise what the system is getting from its surroundings. So as you can see it over here, if I am increasing the wait time, so the contrast is going down drastically. You can uh, so the thing is over here, what we have, so the red one, the Ramsey contrast meaning maximum to minimum, that ratio is the contrast. Now the red plot, what is showing over here, it is like, like most of the, like, so this plot basically showing the coherence time of our system. So when we are using, and it mostly comes from the magnetic coil, in the, if you remember, like in the picture of our setup, there was big coil, right? Helmholtz coil. So that was fixing the quantization axis in our system. So if so those things, how we are generating B field, because the current is flowing through the coil, and then the B field is generating. So if that is not very precise, or it is hitting up the coil, then there will be fluctuation in the B field. If B field is fluctuating, then the Zeeman levels, my qubits, that will also, with all those relevant levels, there will be broadening, right? So that then your coherence, like coherence time, will be lower. But if instead of using coil, if we use permanent magnet, that will definitely improve. That is what it is shown in the blue dot. Yeah, if we use permanent magnets, the fluctuation will be there, but it will not be at that level compared to when we have Helmholtz coil, which is basically copper wire. The other thing is that the other thing of like why we use Raman spectroscopy, to know the frequency precisely, because if we want to drive the qubit, the frequency, phase, and amplitude, these three things are very important. So frequency you need to know very well. Otherwise, there will be infidelity in git preparation, also in implementing, also in step preparation. Everything will be, the fidelity will be very poor. So in order to know the particular frequency or the center frequency of the carrier, we usually do Ramsey spectroscopy. On the right hand side, you see the fringe that is called Ramsey fringe. The carrier in the black colored one is the carrier, but if we use the Ramsey spectroscopy, then we can see the fringe and we can identify which one is the center fringe, and so we can follow that frequency, and that is basically in hertz level. It depends on whether it will be hertz or kilowatt. It depends on the laser what we have developed, what is the bandwidth, how well it is stabilized. So for this qubit laser, the cavity what we are using for locking the laser, that is very ultra stable cavity. The mirror which usually form the cavity, usually high finesse one. Okay, so actually we reduce the line width of that laser to 100 hertz by locking to that ultra stable cavity. So this is the Ramsey spectroscopy. Now I was talking about like loading ion is not, or having more qubit is not a problem at all in trap dial platform, but controlling them individually, manipulating them, that is difficult. So this is, so I'm discussing, talking about linear power trap. There is another kind of trap dial platform is pairing trap, which use magnetic field for trapping. So there it is possible to load even 1,000 ions. So this is actually 700 or 800 ions they have loaded. And you can see it over here. This is the group in USA. Now, I have shown you the picture of first classical computer. Now, this is the picture of today's available quantum computer. It is kind of two racks. One rack is having all the control electronics, lasers, optics, optomechanics, and the other one will be having the vacuum chamber. Inside is a trap or qubit, and they both the racks are connected through fiber, so that you can have light going from one rack to another rack. And this is the kind of trap people usually use. This is quite different compared to the trap what I was using, that is 3D trap, and this is chip trap, but 3D chip trap. Yeah, this is, I mean, only a few groups they work with this. It's very difficult to procure this kind of chip trap. Okay, now I'm going to tell you one of the application of quantum computation is data classification, because you know the data classification is I mean is we used to do in everyday's life, like human being, machine, those machines which are automatic, then it will also classify. So you have to you have to train your machine so well that it can classify whatever be the work it is doing. So we actually trained ourselves from childhood, right, to identify, like from our perspective, from learning. So that is how we used to classify. Classification is everywhere, like from medical imaging, as I have pointed it out over here. You can see the application of classification from medical to data analysis, different kind of data analysis. Everywhere is classification. How well you can classify. Now, why I'm talking about this application? Because we use classical computer. The problem is not to classify very easy things like binary problem or like these animals. These are very easy because the feature space, like for each animal or this kind of shapes, these are easy to classify. But whenever you go to data or this kind of fingerprint, then it is not easy. Easy in the sense it is time consuming, it is not fast, it is not energy efficient. So that is why quantum computer comes. It will be faster and also cost effective. So that is the one important thing why we should develop quantum computer. The in that respect, so the way so if you were to classify, nowadays we are using classical computer, so we know how we trained our classical computer. I'm not expert in neural networks, but networks people usually use for like in classical computer to classify things. So how are you going to use that thing in quantum computer? Because first you need to train your quantum computer, then you can test whether it can classify well or not. But the way of data uploading is completely different. In case of classical, it is very easy, right? Like I can give you an example over here. Like I want to classify, I can take this problem, the binary problem. I want to classify how many points or which points are inside this circle, like the blue points, and which points are outside the circle, like the orange points. How to classify those two class A and class B, the points which is inside and outside. Now, as a human being, we are trained how to classify. We know, so the circle radius is given, the center of the circle is given. We can get the coordinate of each point, and we'll get the radius, and we'll compare the radius of the circle. Then we can calculate analytically, right? But how machine is going to train? Machine cannot do all these things, right? So that is why you have to train first quantum computer. But now how are we going to upload the data? So the way we have to upload only by angle theta and phi on quantum computer, right? As you can realize in the block sphere. So those all these are rotational gates, unitary operator. So you have to convert this all the data points, all the coordinates of the data points, like x1 and x2, convert it to theta and phi, so that you can apply rotational gates. So that is the way to upload the data on the quantum computer. Now, if you want to classify this binary problem, what I just told over here, what I'm going to do. So the way I'm converting this data to angle, I'm following some answers. Okay, there are a different way of mixing this data into the into theta and phi. So I'm using this one because this one was giving me higher accuracy in classification. That is why. And how we're going to once you have this kind of answers, then you can construct your quantum circuit, which is shown over here. So the circuit will be having two rotational gates, RY and RZ gates. Now here I have also mentioned L. L is layer. So now the way I am uploading the data layer wise. So first each layer will be having two sets of rotational gates, okay, RY and RZ. Now I upload this layer 1 and I will check the accuracy, how well it classifies. How I'm going to do that thing? You can see over here, data processing with re-uploading. Like you upload L1, meaning it's a theta and phi. So that you apply, like you can see here in the animation, L1 is applied. You prepare your system in zeros, okay? Then you applied layer 1. So it will end up in somewhere on the block sphere. Then you measure it. This is the quantum state measurement. You measure it, then you know where it is, right? So now you are defining that those datas, or like when you are measuring where it is on the block sphere, it divided into two parts, like which will be on the top side, close to the zero side, they will be class A, and which will be the one, like get one side, that will be class B. That is how you are training. So then you can say that is class B. Now you applied L1 and you try to find out the accuracy, how much it is. If it is not good enough, you apply again another layer, L2. So, and all the layers, as I was saying, consist of rotational gates. So that is how you are improving layers repetitively, and you are measuring the accuracy of classification, whether it is improving or not. So here what we have done, so so this is basically, it is not completely possible with classical, not quantum computer. So first you need to train your, so there are two processes. One is training, another is validation. The way you train, whether the train is good or bad, that will tell you when you verify with unknown data set, how much accuracy you are getting. So for training, initially what we use classical computer. So from the training, from the classical computer, we got the value, this optimal value theta. If you see theta over here, this theta, actually I'm talking about the theta here. You see this theta 0, theta 1, theta 2, theta 3. These are the optimal parameters which I am getting from training. And now the data is over here, x1 and x2, as I have mentioned over here in the problem, x1 and x2 are the coordinates. So that is how you are converting your data with optimal parameter and converting it to angle. So from training, you got theta, and now you are verifying with quantum computer what is the accuracy. And what we found, you see, this is accuracy, it is close, but it is not as good as classical computer because of this optimal parameter, the parameters what we got from classical computer. The training we have done in classical computer, but the verification we are doing it on the quantum computer, taking the optimal parameters what we got from the classical computer. So that is the discrepancy. So that is reflecting over here, where in this feature space you see the theta 1, theta 2, what we are getting, the minimum So this one, we are thinking that this will be the optimal parameter for quantum computer, but that is not true. That is reflecting over here, as you can see. For quantum computer, the minima is over here. Theta 1, theta 2 value is supposed to be here, but it is not true. So that is why the accuracy, if I compare with the classical one, it is close to the classical computer, but not close enough to compare. So that is why we need to train quantum processor. Now, training quantum processor is really challenging. There are many things which are there, need to take care of it. So there are three things here. One is we need classical computer definitely. We need middleware, like in order to communicate to quantum computer, you need middleware in terms of like FPGA, DDS, like the way you can generate frequency and all these things. And then on top of that, there is a some electronics, optomechanics, and then our ion trap system, which is quantum computer, right? All these things you are familiar with, like in order to drive the whole system, those quantum systems, quantum computer systems, you need all these things. So then this is very difficult because now you are communicating CPU and QPU. QPU is basically what I mean, quantum processor. And through this where now there are many things because you have to upload the data will come from classical computer. So it is really challenging and time consuming. But we have done that thing and we train our quantum processor. So here you can see the algorithm what we use for training is genetic algorithm. And here you see like over the generation, if we do it repetitively, the accuracy is increasing. And this is the result. Like after training, what we did, we take 1,000 data set, unknown data set, and we use our quantum computer to validify what is the accuracy. When we upload the data only once, that is the accuracy. You can see this is the how it is classifying. Very simple binary problem. But when we upload two times, the layer two times, you see it is improving, and four times it is almost good. So yeah. So you see now after four layer, the accuracy, classification accuracy is almost close to the CPU, and the error bar is not there, but it is within the error bar. So we have not done. So we have done not only this binary problem. We tried with many other problems like multi-class problem, like multi-class, multi-dimensional problem, and different kind of feature space we have tried, and we compare with the classical algorithm, and we compare that it is exactly behaving same with the classical computer. But the important thing is that for this classification, we use only single qubit. So how powerful it is single qubit? It can classify this challenging classification problem. So I am kind of close, so I will not go into the details. But so that is one application of quantum computation. Now the another application is you can use this platform as a quantum sensor. Now what I was telling, the like if you want to know the frequency, you have a two level, right, and you are driving it. So this one you can think of it as an atomic clock, right? Now you are driving it. Now you need to know the frequency very well. Very well meaning precise. So the accuracy and precision, two things are different. Okay. So for the atomic clock or for driving this two level, it has to be accurate and precise. But all of us know that it is limited by Heisenberg uncertainty principle, right? So here omega is the uncertainty of the frequency, and it is limited by 1 over 2t. T is the observation time or experimental time. Similarly, similar kind of example we can take, like magnetic field is there and spin is there. So spin will start precessing around. Now, how do you know that the frequency it precesses? If magnetic field is modulating 1, then it is very difficult because the precision is limited by uh, 1 over t. So you cannot go beyond this. But the beauty is over here. This is time independent Hamiltonian when you're talking about Heisenberg uncertainty principle. But in quantum metrology, we can take time dependent Hamiltonian, and then we can talk about quantum physics information, and then we can show that we can go beyond this Heisenberg limit. So the sensitivity will become 1 by t square, not 1 over t. I'm not going into the details. So here also we are in order to implement, we are using the similar kind of pulse setup, the setup we use for Raman spectroscopy. But here in between, during the wait time, we are using modulating pulse and control pi pulse. So that is how the way we are implementing it. So, and that is also, this is also published work. Whoever has interest can have a look. This is really nice work because it has a huge implication. Starting from searching dark matter. So this is our experimental results. Like the uncertainty is proportional to 1 over t square when we are considering time dependent Hamiltonian, and 1 over t is when it is independent Hamiltonian. So it has a huge, as I was saying, it has a huge impact because it will help us to detect dark matters like axion-like matters, and also we are developing atomic clocks and the sensitivity is 10 to the minus 19, but still it is not high enough. Why? Because of our ignorance of noise. Okay, so this method will help to find out the noise frequency, then you can remove it. So that is also another importance of this method. The other thing is like, now we all have mobiles, right? It is connected to the GPS. Now, if you are moving, a mobile is moving, right? If you go to other place, how it is connected so that you can see the time, particularly on that space where you are, because it is connected to the GPS. But how accurately it is giving the time to you, that also matters. So that is how it is related. So this is one aspect of this platform that you can use as a quantum sensor. The other one is simulation, quantum simulation. So here I'm just briefly telling you about this is what I have done. Like I was talking about laser and interaction, right? If you see the Hamiltonian, this Hamiltonian actually James Cummings Hamiltonian, if you remember carefully. But this Hamiltonian, you can tune it and you can describe it by an effective Bohr-Savart model. If you can describe Bohr-Savart model, then you can see different exotic things what people have seen for atoms like Mott state and superfluid state, right? Here Mott meaning all the ions in your trap will have similar number of phonon. So, and that why it is very important, because we are talking about having more number of qubits. When you are going to have more number of qubits, you have to keep it cool, right? Now, always you cannot apply different cooling method to bring it to the ground motional state. This method is very important because here, let's say you have 100 qubits, but one qubit will be completely used for this kind of like if you want to implement this thing, we have to dedicated one ion where we will apply this particular potential, and we will change the potential. So by changing the potential, what is going to do, like rest of the ion will go to the ground state except these ions. Like these ions will eat all the phonons from rest of the ions, sending them to the ground state. So those ions can be used for uh, like for our experimental purpose. So this has not been implemented yet, but you can see in the animation over here, right side at the bottom, like all the ions going to particularly in one state, all the phonons particularly going to one ion. So what is happening over here, the addressing layer, the phase of the addressing layer is changing, particularly at that ion side. It is going from antinode to node. So by that way, you can have Mott state. So this is also another important thing that you can perform using this trap dial platform. So yeah, this is the experimental result. So I'm going to stop here. Thank you.
It was
One time, I
really
guess.
one experimental things, because in quantum thing, most of the time we see only the simulation part or the theory part. So yes, so let me go through some more queries are there. And Satyendra Prasad, he want to know where these lab or such type of machines are
Oh, okay.
available currently in India.
Okay.
So
Whatever that he presented, it is during my PhD and not PhD, in my postdoc, like last 5 years. So I joined here last year. So we want to develop similar kind of setup over here, waiting for fund. We started already doing few things like locking lasers and all these things. Yeah, hope we'll be doing it soon.
yeah, very soon maybe. We
Yes.
wish that you get everything ready here also.
Yes, I will definitely try. I mean, yeah, I will. Yeah.
Yeah. So K. Lakshmi Narasimha Rao, he actually mentioned somewhere in time that are you referring to QML? I think quantum
Oh,
machine
quantum machine
learning.
learning. Yes, yes, quantum machine learning. Yes.
Yeah. So overall, everybody is writing nice session, and thank you to you.
Yeah, I mean, whoever has interest, I mean, can go through the paper, or you can ask me in my email. So, I mean, I'm always available. I can reply. Yeah.
Yes, actually, it was very fascinating to me also. So because uh, it is. Can you comment where else in India other groups working to make such qubits or trapdyne based
Okay,
systems?
so I mean, in India, nobody is working in this level with ion trap. Only in Aizer Pune they have started, but nowhere I think there is. But there is superconducting qubit is there in IIT Bombay. Optics experiment are there in India, but trapped ion not at that level. Only Aizer Pune one guy started. Yeah, but that is still in basic level. So that is what I know.
Yeah. Okay, sir. Thank you so much. And
Yeah.
I also thank all the participants for
Thank you
a
all.
nice
Yeah.
interactive session. Thank you, sir. Thank you so much.
Thank you. Thank you very much.
Okay, sir. Bye.